Hello, I'm Ethan from Team 7588 Cat Lateral Damage. This video goes in-depth on AprilTags and the available tools for the 2023-2024 FTC game Centerstage. This video picks up with our AprilTag Quick Start video's op mode. I recommend checking that video out first if you have not already. For this and the past videos, I've been using screencopy to see the control hub screen, which is my preferred method over an external monitor. Screencopy allows you to mirror your Android phone's screen over USB or Wi-Fi, allowing us to see what is on the robot controller. The link to this page can be found in the description. From here, click on the latest release, and assuming you're on a Windows PC, download this file. From here, extract the zip file to a location that you will remember. Then open the folder and run scrcpy or screencopy.exe. Now you should see the control hub. This is assuming that you are plugged into or connected to over Wi-Fi the control hub. If for some reason this does not work, you can also open a terminal here .bat and type scrcpy. This should bring up the control hub. If we have multiple devices plugged in, then we can select which one we want to launch by typing scrcpy, and here we see both the devices and their serial numbers. We want to look at the control hub, so let's copy this, and then type scrcpy-s, and then paste in that value. Now it should open the control hub. Let's define a couple terms before we jump into the code. Quaternions are another method of describing rotation in 3D space. Euler angles can suffer from an issue called gimbal lock, which removes a degree of freedom, so the FTC SDK uses quaternions instead. They use 4 values to describe rotation, and the math and reason behind that is far beyond the scope of this video. If you want to learn more about quaternions, I recommend checking out 3 Blue 1 Brown's video on them, which is linked in the description. FTC has a specific absolute coordinate frame that is used throughout the SDK. When standing in the red driver station, positive X is to your right, positive Y is away from you, and positive Z is up. The origin of the field, 0, 0, is in the center of the field. The AprilTags used in Centerstage will be from the 36H11 family. The 36 corresponds to the number of pixels within the black box, while the H11 corresponds to the Hamming distance, which is the ability for error correction when identifying tags. The higher the number, the less likely you are to get incorrect tag identification. This tutorial will go in depth into many of the features of AprilTags provided within the SDK. AprilTag detections, VisionPortals, and AprilTag libraries all use builder patterns to chain methods and streamline the process of creating these classes. If you have experience with Roadrunner, creating trajectories uses the same builder pattern concept. For example, each method after AprilTagProcessor.builder returns a builder object, while the .build method converts the builder object into an AprilTag processor. Let's look at all the rest of the builder methods for AprilTag processors that we have not implemented yet. First, we have .setLensIntrinsics, which takes an fx, fy, cx, and cy value. This tells the processor how the camera interprets the 3D world. Some common cameras and resolutions use pre-calculated lens intrinsics from the SDK, but you may need to calculate lens intrinsics yourself if you need to or dislike the pre-calculated intrinsics. To learn how to calculate these intrinsics, I recommend our camera calibration tutorial, which is linked in the description. Next, we have .setNumberOfThreads. I recommend not using this method unless you know what you are doing, as messing with threads can easily cause issues if not used correctly. If you're curious, the default threads used is 3. SetTagFamily allows you to set the tag family. Only 36H11 tags will be used in Centerstage and are the default for AprilTag processors. Finally, we have AprilTagLibrary. The SDK has 3 libraries pre-implemented that you can choose from. The Centerstage library has tag IDs 0, 1, and 2 at the size of 0.166 meters, or roughly 6 inches. The sample tag library has tag IDs 583, 584, 585, and 586. The first two are 4 inches, while the second two are 6 inches. The current game tag library is the default and contains both the Centerstage and sample tag tags. These libraries will be updated when Centerstage releases. You can also create your own library, which I will talk about later. Now let's look at the methods that the tag processor has to offer once created. We talked about get detections in the last video, but there's also get fresh detections, which only returns a list of new readings. Set decimation allows you to set a custom decimation value. A larger value means a higher frame rate but lower range. Set pose solver allows you to choose from several different ways of calculating the tag to camera pose. I'll leave it to you to experiment with different solvers and their behaviors. Get per tag average pose solve time returns how long it takes to retrieve the tag pose using the active pose solver. Some pose solvers take much longer than others. Now let's look at the unused methods for VisionPortals. Enable camera monitoring enables camera monitoring on the robot, as we have in past videos. We will take advantage of this feature later again. By default, this is set to true. Set auto stop live view automatically disables the live view if you disable a processor to save resources. By default, this is set to true. Set camera monitor view ID is only needed if you are using several cameras. This will be covered shortly. Set stream format allows you to set the stream format to either MJPEG or YUY2. YUY2 uses more bandwidth, but supposedly has increased speed and quality, while MJPEG has reduced quality but far less bandwidth. I will leave testing up to you, but in my experience, MJPEG at 640 by 480 functions well. By default, this is set to YUY2. Now let's check out the methods for the VisionPortal. .getCameraState returns the current camera state. The camera can either be opening camera device ready, starting stream, streaming, stopping stream, closing camera device closed, or error. This can be useful to ensure the user does not start the op mode until the camera is streaming. Gets active camera returns the active camera object you passed in when creating a VisionPortal. Get camera control allows you to control a parameter of the camera. We will use this later to tweak the exposure and gain. Get FPS returns the frames per second of the camera. Get processor enabled returns whether or not the given processor is enabled. Set processor enabled allows you to enable or disable a processor. Close closes the VisionPortal and processor and cannot be undone without restarting the op mode. Stop streaming and resume streaming stops or resumes the processor from retrieving and processing images. However, it takes a couple seconds to stop or start, so frequently stopping and starting is not recommended. Stop live view and resume live view function the same way, but for the live view on the robot controller. Save next frame raw allows you to take an image and save it onto the robot controller. A VisionPortal MultiPortal allows you to use more than one camera at a time and display them both on the robot controller and control hub. In order to utilize 2 cameras, you will need 2 processors and 2 VisionPortals with unique cameras. These VisionPortals require certain camera monitor view IDs. To create the MultiPortal and get those IDs, start by creating an int array, which I will call portals list, and say equal to VisionPortal.makeMultiPortalView, however many cameras you are wanting to use, in this case 2, and the layout, which we will be doing horizontal. This returns 2 camera monitor view IDs, which can be used in the creation of the VisionPortals. Now we just create the 2 tag processors and the 2 VisionPortals, and for each VisionPortal, we're going to put in one of the tag IDs by calling portals list bracket 0 for the first ID, and then portals list bracket 1 for the second ID. Now you should see both cameras on the robot controller. A single AprilTag detection holds all the data about a single tag and what the camera saw of that tag, including relative pose, tag location, ID, and more. Tag.rawPose returns the raw pose values, including the X, Y, Z distance, and a 3x3 rotation matrix. I recommend not using this as it does not follow the FTC coordinate frame like FTC pose does, which we explained how to use in the previous video. Tag.id simply returns the tag ID, which can be helpful for many reasons, such as if you only want to line up with a single tag even if you see several. Tag.center returns the pixel coordinates of the center of the tag on the screen. Tag.corners returns a list of outer corner pixel coordinates of the tag on the screen. Tag.decisionMargin returns the margin of confidence in the tag. If this value is 1, it is 100% positive that it is an AprilTag, but anything lower means it is less confidence. The 36H11 family does not struggle too much, but some families commonly have false positives where this is a very important number. Tag.frame acquisition nanotime returns the time that the reading was retrieved in nanoseconds. This is useful for if you want to ensure the tag and another reading are from the same time. Tag.hamming returns the hamming distance for the tag. And finally, tag.metadata. From here, you can get everything that is included in the AprilTag library about the tag, including the name, ID, distance unit, field orientation, field position, and tag size. I want to talk real quick about the field orientation and position. The field position returns the vector f class, which contains the x, y, and z values. To get these values, simply say .get, and then 0 for the x-axis, 1 for the y-axis, and 2 for the z-axis. Next, the field orientation. This returns a quaternion, which describes three-dimensional rotation using 4 values. Again, if you want to learn more about quaternions, I highly recommend you check out 3 Blue 1 Brown's video, which I've linked in the description. To use this quaternion, just look up a conversion formula for quaternions to Euler angles. AprilTag libraries allow you to create custom libraries of AprilTags with a custom size and location. To make an AprilTag library, start by creating a new class and call it something like AprilTag Custom Database. Within this class, each library will be represented by a static method. I have 2 tag boards, both with AprilTags, one with 6-inch tags and the other with 3-inch tags. So I will make a library for my small 3-inch tags. This method will return a new AprilTagLibrary .builder, and then we'll finish it off with .build. Now we can start adding tags between these lines by typing .add tag. From here, we have 2 primary ways to define a tag. The first option defines the ID, name, size, and distance unit. Here it places the tag as 000 with no rotation. Alternatively, if we want to place the tag in a specific spot, we can also add a field position and field orientation. The ID just refers to the ID of the tag. The name is the name of the tag, which can be whatever you want. The size of the tag is the distance from one black edge to the other. The units are determined later. The field position is where the center of the tag is on the field. This takes a vector f class with 3 arguments for x, y, and z. Now we set the units. We can either use inch, millimeter, centimeter, or meter. This applies to both the tag size and field description. Finally, we set the field orientation. This requires a quaternion. You can either use conversion formulas for a custom orientation or reference quaternion.identityQuaternion, which assumes Euler angles of 0, 0, 0. You can also add a default library by adding .add tags and then referencing one of the pre-made libraries. This library can now be used by typing the class name .getSmallLibrary. Instead of typing out telemetry.addData for each value and cluttering up the driver station, I'm going to type telemetry.addLine. And then in here, type String.format. .addData expects a string and a value, while addLine only expects a string. String.format allows you to convert values into a string and format them nicely. For this line, we will print the x, y, z values together. I'm going to type xyz followed by %6.2f and then just repeat that another 2 times. The percent sign references a value, while the 6 represents the spacing from the previous character, and the 2 represents how many decimal digits to round to, and the f refers to the variable type, in this case a float. After the string, we need to add the xy values that should replace the percent signs. In this case, is tag.ftcpose.x, tag.ftcpose.y, and tag.ftcpose.z. This is extremely useful as it makes the data more compact and allows you to have more telemetry on screen. You can also get rid of this warning by hovering over it and clicking Suppress Default Locale with an annotation. You may have noticed that as the robot moves around, the readings either become less reliable or disappear altogether. This is because the tag appears blurry due to high exposure. If you do not know, exposure is how long the webcam's lens takes in light for an image or a frame. The lower the exposure, the less motion blur occurs, but with the drawback of a much darker image. Darkness can be combated by increasing the gain or the brightness of the image. This allows for more reliable and consistent, but not perfect, detections while moving. The SDK provides several webcam controls that allow for manual adjustment of these values. First, we need to ensure that we don't crash the out mode by attempting to access webcam controls before the camera is streaming. After we create the tag processor in VisionPortal, I'm going to accomplish this by creating a while loop with the condition VisionPortal.getCameraState, and when it's not equal to streaming. Now, the op mode will hold in this while loop while the VisionPortal is starting, and once the camera starts streaming, it will continue. Now let's start with exposure. Type exposure control, I'll call this just exposure, set equal to the VisionPortal.getCameraControl, and in here type exposure control.class. Now with the exposure variable, we can customize the camera's exposure. First, I recommend printing out whether or not exposure is supported. You can do this by typing exposure.isExposureSupported. If this returns false, then your camera unfortunately does not support exposure control. If it returns true, then it does support exposure control. If it is supported, then let's set the mode up here to manual. And then on a new line, set the exposure to a low number. Do this with exposure.setExposure, and we'll say 15 and define it in milliseconds. Now the exposure is set to 10 milliseconds every frame. Next, let's change the gain to counteract the darkness from a lower exposure. Similar to exposure, we're going to type gain control gain equals VisionPortal.getCameraControl gain control.class. For gain, I recommend printing the min and max gain values to know what the max gain value is. For the C920, which I am using, is 255, and you can set it with gain.setGain 255. Now you can test different exposure values to see what gives adequate brightness with minimal blur. Keep in mind that tweaking exposure and gain values may make you more prone to unique behavior under different lighting conditions. Most of the content in this video is explained in FTC docs, which is linked in the description. This video covered the new AprilTag features in the SDK and provided some helpful additional tools. If you have not already, I recommend checking out our AprilTag Quick Start and AprilTag Camera Calibration videos. If you have any questions, feel free to comment or reach out to us via Discord or email, or look for help in the FTC Discord server. My Discord username, our team email, and a link to the FTC Discord are all in the description. Thanks for watching! Here, we can just select the op mode and start it up. And look at that! It's spitting out a bunch of numbers. As I physically move the April tag, are you kidding me, Ernie?